Okay, so we're talking about physics, light, quantum mechanical model, a whole bunch of interesting things in this chapter. The first thing we're talking about is the history. So you have probably heard of Isaac Newton, right? And Newton thought that light was made up of particles. And that's partially true. Light exists in both particles and wave form. So it has this interesting thing where it can act like both. But in the beginning, they just thought it was particles, and then we started to see things where it can act like a wave as well. So before we get much further than that, we need to talk about what a wave is. And you've probably been to the ocean. You know what a wave is, right? Which it's very similar to what a wave is as well here. You ever go out a couple feet into the ocean and you just stand there and then the waves just kind of come up and then down and then up and then down? You're just chilling, right? We're imagining June or July, not in school. It's a good time. Well, the same thing happens with waves. Waves do the same thing. They go up and down, and that's called oscillating, going up and down, kind of like in this way. There are distances between the tops of two waves, and it's a distance, so we call that the wavelength. All right. There's a Greek letter here. It's an upside down Y. It kind of looks like. It's called lambda, and the distance between these two waves is the wavelength, and that gives the wave all of its properties. If it's really far apart, doesn't have a lot of energy. And you can think about that on like in the ocean. If the waves are really, really far apart, it's very slow, it's chill, everything's cool. But then you could also have waves that are really close together, right? And that seems like it has more energy. It would move you around a lot more. That would be a shorter wavelength because they're bumping a little bit more, and that would have more energy, all right? We'll talk more about it in a couple minutes. There's also how fast the waves are moving. And all waves in a vacuum move at the speed of light, which is a very, very fast speed. You can't go any faster than that, although there are some scientists and some physicists working on faster than light things right now. All right, so that's a little bit of the history. Have you seen this before? Yeah, right? The electromagnetic spectrum. Okay, so here we show all the different waves, all right, wavelengths and whatnot. And this is broken up by their wavelength in meters. So these are extremely short or tiny wavelengths to the negative 12th meters. And then they go all the way to very, very large, or 10,000 meters, all right? So this would be, that means that it would take 10,000 meters for it to go up, down, and then back up again, all right, to the same spot. These, it would be so tiny, you know, we obviously couldn't see it. It would be really, really small. And then here, this one would be 1 meter. So if you think about a meter, maybe it's from here to here, that means that it would go up and down within about that same space in there, all right? So there are all these different wavelengths, and based on their wavelength, you have different properties. Does anybody know any properties of, because we're gonna do at least one property of each of them. Anybody know any properties of gamma rays? Where you've seen gamma rays before, where you've heard of them? Could be in the real world or in science fiction. Yeah, Scotty. Yeah, the Hulk, right? So with superheroes and whatnot, you hear that they get hit with gamma rays and then it changes them into superheroes. How does it change them into superheroes? How does it give them their powers? What is it doing? It's mutating them, right? It's mutating their DNA, and that's giving them these different powers and whatnot, right? Which sounds awesome. What's more likely to happen when we have a mutation? Yeah, we get cancer and we die. Exactly. Yeah, so that's what gamma rays, they have the most energy. So we're going to write that down, most energy. They'll mutate your DNA, which again isn't a good thing, all right? Now, this is a form of ionizing radiation, which means it can cause ions and damage to DNA. X-rays can also damage your DNA, but they have less energy. And even ultraviolet can damage your DNA as well, all right? Where do we see X-rays used often?
The dentist.
Dentist, yeah, hospitals, exactly. So I'm just gonna write medical, all right? And it allows us to see bones and harder tissues and whatnot. So you can use the medical things for x-rays. What about ultraviolet? What's the abbreviation, first of all, for ultraviolet? Yeah, UV, good. Where do we see this?
Sun.
Yeah, the sun, right? The sun. What else does the sun give us? Cancer, yeah, I guess you could talk about the UV and whatnot, yeah. But does the sun give us visible light? Yeah. So we can't just say UV is the sun, right? Because the sun also gives us visible light. Does the sun give us any of this other stuff? Infrared? What's infrared? It's IR. It's heat. The sun gives us heat, right? So we can't say the sun for ultraviolet because the sun actually gives off all of them, all right? Now, it doesn't give us radio stations, but we can hear radio waves from it and whatnot. All right, but when you said the sun, what were you really talking about with UV?
UV rays.
UV rays, yeah. And what does it cause to happen to you? Skin cancer, right? Skin cancer. Remember, all of these cause mutations in DNA and whatnot in high enough doses. So yeah, UV, skin cancer, all right? So that's not great. All right, what do we use to protect ourselves from this?
Sunscreen.
Yeah, sunblock or sunscreen. Good. Okay. UV, a lot of energy. Visible, we know visible, right? It's the only part we can see, right? It's the only part that our eyes can pick up. Why don't you think our eyes can see gamma, X-ray, or ultraviolet? Why didn't we evolve to see those? Scotty, what do you think?
It's not necessary for our survival.
Okay, not necessary for our survival. And Ajwa, you're right too. We can't evolve to see these, or we didn't evolve to see these because they damage us, right? So if you're looking at a lot of this stuff, you wouldn't have lasted too long, or you know what I mean? UV, there are some insects that can see ultraviolet and infrared, and you might have seen flowers and pictures of flowers and stuff under UV and infrared, and they can be quite beautiful, and they're attracting pollinators because of those different kind of views. Okay, so that's ultraviolet. Visible we can see, which is great. Infrared, IR, that's heat. So if you've ever heard of like heat lamps, either for like fast food restaurants or sometimes bathrooms, fancy bathrooms have these. They're like red lights that just, when you turn them on, you just feel warm. If you have like lizards, reptiles, that kind of a thing, you might need a heat lamp to keep them warm because they're not warm-blooded. All right, and then there's also microwaves. And what do we know about microwaves? They're probably your favorite out of all these, right? What are microwaves? You're like, food. Yeah, you're right. They heat up food, right? How do they heat up food? With microwaves. Yeah, that's good. That's good. What do they do to heat up the food? Yeah, they're microwaves. They rotate water molecules. And whenever you rotate something, causes some friction. So there's friction between these water molecules. So think if you rub your fingers together, your fingers will get warm, right? The same thing happens with the water molecules. So when you're rotating water molecules, that's causing heat, which heats up your food. And that's why microwaves are really good at heating up liquids. So soup, coffee, tea, that kind of stuff, water, you put water in there, it heats up real well. You put in like some dried out something in the microwave, it won't heat it up as well. So when you guys go off to college and you become experts in using microwaves, your culinary skills improve for microwaving. Just remember, a wet paper towel can do wonders. Put that on there, it has water, it'll heat up the food better. Drip a little water on your food, put it in the microwave, it'll heat it up better because you're adding more water in there, all right? There you go. Okay, so microwaves, rotating water, that's great. What about radio waves? Sound, yeah, sound. You can think of them as sound and whatnot. Now, we can't actually just hear them, right? Like when we're walking around, we don't hear like radio stations in our head. That would be weird, right? We need a way to translate them from energy into sound so we can appreciate it. All right, but yeah, you're on the right track there. What's the difference between FM and AM? Music versus boring talk shows. Yeah, which one's the boring talk shows? AM. Music's FM, right? Why do you think FM was picked for music? Why do you think AM? What's that? No, there's a good scientific reason for these. Why would FM be better for music and AM just be for boring talk radio? Audra, what do you think? Yeah, it has to do with the frequencies. So why would AM be better for just talk and FM better for music? More complicated, higher fidelity, right? It sounds better.
It's a lot clearer.
It's a lot clearer. Why? Why is FM clear? Why is it better? When we're looking at this spectrum, what do you think? What did we say energy-wise on this side? More energy, right? So what do you think as you move across is happening to the energy? Less. There's not enough energy to mutate our DNA on this side, right? There's lower amounts of energy. This side has the least amount of energy. So with energy, it's the least amount. Music requires a certain amount of energy, right? As opposed to talk radio. And maybe just, it kind of makes sense, right? AM probably has more monotone, not a lot of energy in there. FM, for the clarity for the music and whatnot, that would have more energy. So it's going to sound clearer, sound better with the more energy there. All right. So there's our two things with radio waves. And another interesting thing is with AM, lower energy, but it can travel farther. So you can pick up like radio stations from New York for AM. But as far as like music and whatnot, we could only pick up radio stations from Philadelphia, which is a little closer to us. So yeah, we get more energy, better clarity, higher fidelity, FM, and lower energy, less range. You get your AM there. All right, cool? Okay, so now we have something for all of them. If you take a look at this visible spectrum, you've probably heard of Roy G. Biv before, right? Roy G. Biv, the whole way to remember the colors. What do you notice about it on this one? It's flipped, yeah, exactly, because on this one, we go from wavelength, from the shortest wavelength to the longest wavelength. So that's why it's flipped here. It's, you know, Viv G, or your, going in that direction. Now, why should you remember this? Because again, if you have this as a handout for a test or a quiz, it might be in black and white, so you're gonna wanna remember which way the colors go. But notice all the colors, they're all times 10 to the -7th. And this goes from -12th all the way to the +4th. So there's a huge range, and we can only see a very, very tiny part of it. All right? Okay, any questions with any of that stuff on there? No? All right. Which color has the most energy?
Red. No, blue. Violet.
Yeah, violet, right?
Violet.
Over here, the violet has the most energy because it's on the left side, right? And we said that this has the most energy. And then red would have the lowest amount of energy, right? All right. What would have the most overall energy out of everything? Not colors. Well, it could be a color. But gamma, right? Because it's times 10 to the -12th. So that would have the most energy overall. This is only to the -7th. All right. What would have the least amount of energy overall? Yeah, AM radio waves, right? Because it's 10 to the 4th here. Yeah, exactly. Good.